All right, well, here we are again. It's a pretty miserable Wednesday morning, but at least we're all safe inside right now. God, I don't know how bad it is down there at Purchase, but well, you know, we didn't lose our power. That's the most important thing, I think. So, all right, anyway, so what we're going to do first today is look at the chapter 4 problem sets. And so let me go get Moodle open. Let's see, here we go. And when that's done, we can carry on with chapter 5, which is our discussion about trigonometry. And then I think there's 1 or 2 videos that we might have time for as well. They'll help, hopefully try to help us understand more about what we're doing with the trigonometry, which, you know, let's face it, it's a very complicated topic. And it's possible that, you know, you haven't thought about this in a long time. And but also we're hoping that you'll gain some new insights into the relationships between these different measures and what they can be used for. If you do decide to go on to Calc 1, you're going to see these more often as part of the curriculum. You know, a lot of examples will be based on trigonometry, trig functions. And so it's important to get more background in this area. All right, here we go. So we'll download the chapter 4 problems. There they are. Now, this is still based on 4, of course, with logarithmic and exponential functions. All right, first let me save this. Oh, wait a minute. Hold on 1 second. Ooh, you know what? I just realized something. I think I had 2 of them, and I may have forgotten to post 1 of them. I mean, that's all right. We can certainly do them next week, but I'm just annoyed at myself for doing this. Yeah, there were 2 of them. All right, I'll tell you what, let's do this then. As for right now, let's just do the first one. Well, actually, you know what, there's no reason, but you know what, I'll tell you what. We don't want to have to come back to this later on. I'll tell you what, let me post this right now. And that way we can do them both right now. We might as well just do them. There's 2, which I didn't even realize when I posted this. All right, let me get this straightened out. What's going on? Well, any guesses on where it went? Let's try that again. Unbelievable. All right, so let's put them all together in one place. So there are 2 of them. All right, so this is the first one, as I just downloaded it. And oh God, where is it? And then the second one that I just posted is this one. This is the one that's more involved with solving for logs and exponentials. Okay, so there are 2 of these. And so let's just do them one at a time. Okay, let me just quickly save these. Let me consult with my own solutions. Okay. A lot of graphs I see. Okay. All right, so I want to save these so that I can write in them and you can have all the solutions right in front of you. Today is the 27th. We'll save this one and then we'll do the second one right after. We might as well. There's no point waiting until next week. Okay, now this one, I think it got saved in the wrong spot. Hold on. Of course it did. All right, so finally, at long last, we may proceed. Okay, so anyway, what are we supposed to do here? Now, you know what I'd like to do? I'd like to go get the notes back again too, so you can see where these questions were, or these concepts were first introduced. So somewhere along the way, we showed how to take 2 points and use those to find the corresponding exponential function. Now, we've done this before with straight lines, and it's a very straightforward process, but and here we solve for the growth rate, but I'm looking for, here it is. This is what we're doing right now. So we've got 2 points, and we're looking for the equation of this function. After being told that it is an exponential function, you have to be told that. Otherwise, you might end up, or if you assume that it's a linear function, you'll get a very different answer. So in a question like this, you're given 2 points, and you're being told it is an exponential function. And that means that it has the form f of x equals a b to the x power. Okay, that's very important because if you didn't know that, you'd have no way of finding this function. So let me just copy that in here, just as a quick reminder. Oh, there it is. It's on the next slide anyway. So in other words, given that we have this function, what you're basically doing is you're substituting 1 point into this function. Now, the way it's written, the 6, which normally corresponds to y, is going to be our f of x because it means the same thing. And then this -2 is our x. Now, you can see we still have 2 unknowns here. So we have to do this twice, once with each point, and then we're going to solve with simultaneous equations. And the answers are often very, very messy in these cases. These are not linear functions. We can often end up with some very bizarre functions, but this is how it works with exponentials. Now, here, let's again remind ourselves that the basic form we're looking for is this. Okay. So let's do it like this. We start by making our substitutions. Okay. Hold on 1 second to get my tablet out here, and let's begin. All right, so in the case of 1, 6, we know that x is 1, f of x is 6. Okay, so with that being said, we know that 6 equals a b to the first power, which means that we can rewrite this by simply saying 6 equals 80. All right, so that's it. We can't go any further with that one. What we can do, though, is try the next one. And we'll have 3, 750 which implies that x is 3 and f of x is 750. So therefore, 750 equals ab to the 6th power. Now, what you might want to do first, you probably should think about taking the one that's simpler and rearranging it to solve for either a or b. Okay, so 6 equals ab. Let's do this, solve for a. Okay, and if we do that, it's pretty straightforward. 6 over b equals a. Now, why are we doing this? So we can substitute it into the second equation. And solve for b. All right, so in other words, actually, I'll do this one by hand. 750, since 750 is ab to the 6th power, and a we've just determined is 6 over b. You can see what we've accomplished here. We've gotten rid of the second variable. Now, what I can do now is write this as 6b to the 6th divided by b. Now, of course, b to the 6th divided by b to the 1st is the same as b to the 6th minus 1, or b to the 5th. All right, well then now, of course, we'll do some algebra on this. We'll divide out both sides by that 6. All right, and so, hold on 1 second. 750 over 6 is 125. Okay, nice round number, 125. But of course, we're not looking for b to the 5th. We're looking for just plain old b. So we have to take the 5th root of both sides. Now, you can simplify this a little. Nah, maybe not. I think maybe we could. Well, all right, let's just leave it like this. I don't see that there's any opportunities here for simplifying it. Yes, Fernando.
Couldn't we have square root 6 with 750 earlier, or no?
Do we have what?
Couldn't we like square root it like 7 when it was 750 equals like b to the 6th power? Couldn't we like square that before with that or no?
I'm not sure what you mean.
Like since now like you square rooted 5 from both like you square rooted from both sides to get b by itself.
Oh, we're not square rooting it. This is the 5th root.
Oh, is the 5th root? Oh, my bad.
Yeah. You see, there's the thing, because it's 125 is b to the 5th. In order to solve for b, I have to, what I've done is this. And remember, whatever you do to the left-hand side, you have to do the right-hand side. So why am I doing this? Because this expression is going to just be b, okay? In other words, when you have b, let's say raised to the a power, which is in turn raised to the b power, you end up with, actually, let's not use those letters. They're the same ones. Hold on. Let's try it this way. B to the x power raised to the y power equals b to the xy power. So in other words, by raising both sides to the 5th root, or the 1/5 power, I end up with just b by itself, but then I'm left with this very messy expression, the 5th root of 125. Now, I mean, you can go to your calculator and see if by some miracle that's an integer of some, or, you know, I mean, it's possible, but it's not. So we may as well just leave it the way it is. So b is the 5th root of 125. And okay, so let me just double check this for a second. I just want to make sure that nothing went wrong here. We have 750 equals AB to the 6th power. Oh, you know what happened? I think I may have copied something wrong in here. No, I'm sorry. That's the second one. I was looking at the first one. No, I made a mistake here. This is 3. Sorry, this is meant to be 3. I just realized it now. So that makes a big difference. Yes, I'm glad to see that because this is, let me just get rid of all this. After all that, I made a dumb substitution there. It's supposed to be 750 equals AB to the 3rd power because this is X, okay? So this is the 750. This is the X. All right, well, that's going to make it a little simpler. The 5th power is very difficult to work with, as you can see. But anyway, so the first part is fine. I mean, 6 equals AB. And so we can figure out that A equals 6 over B. And then put that back in the correct now value. 750 is AB cubed. But we've just determined that A can be replaced with 6 over B. So this is going to make things a lot simpler. Because now all of a sudden, instead of what I had before, I've got 6b cubed over b, which simplifies to 6b squared. And now all we have to do is divide both sides by 6. And now it's just a simple square root. Now, and since it is a square root, remember our strategy is always to keep everything as simple as possible in math. That includes these radicals. You can see this one can be streamlined a little bit. This is the same thing as 25 times 5. And that in turn is this. And look, the reason why this is so potentially helpful is because I can rewrite this now. 5 radical 5 equals b. All right, now that's not a very messy expression. But the most important detail now is that because we've already seen earlier that 6 equals AB, here's what we can do now to figure out the value of A. If 6 equals AB, A equals B over 6, 6 over B rather. And then all I have to do is put 6 over 5 radical 5, which again is kind of a mess. So here's what I'm going to do. I'm going to use the following property. I'm going to multiply the numerator and the denominator by radical 5. And this is just for simplification purposes. This isn't really absolutely necessary. But mathematicians prefer it this way. So here I'm going to have 5 times 5. These two, when multiplied together, give me 5. And that's it for A. So therefore, the final result is that A equals 6 radical 5 over 25, and B is 5 radical 5. Now, again, remember, these refer to components of an exponential function. So remember, that's written as, from the top, let's go grab this again and make the substitutions. And finally, when all the dust is finally settled, you'll see that our final result is f of x is 6 radical 5 over times 5 radical 5 to the x power. And that's it. Now that's a ghastly looking formula, but that is what we're looking for. Now, if you're curious to see what this looks like, we can always go to our friend Symbolab. And, we've discovered from experience that, it works well much of the time. I wouldn't say that it always works well. It's come up with some very bizarre graphs for us in the past. But it's free and it works well most of the time. So watch this, f of x. Now, this is going to be a challenge to type it, let me tell you. Maybe it's not that bad. 6 radical 5 over 25 is multiplied by 5 radical 5, all raised to the x power. All right, so let's see what it can do with that. Oh, well, it's actually a very nice looking graph, isn't it? Considering how ridiculous it looks, and there's our intercept. And that's, in other words, remember, this a represents the value of the function when x equals 0. And that's exactly what we'd expect to see. And since a is positive, that means that we have this upward sloping exponential curve. And we were given 2 points of this curve. Remember, way back at the beginning, we were given 1,6, which is about here, right there. And the other one, well, you have to go up quite a ways to find it, but 3,750. Actually, I guess we could, if we're really dying to see it, we could probably, well, all right, it's hardly worth our trouble, but you get the idea. All right, so they're all the same. Okay, so let's do that again. Let's see, so you get the 2 points. So just remember what these mean. So let's copy this. Should always have that in front of us. And so in the first case, this implies that x equals 1, f of x is 2,000. Okay, so when you plug everything in, you'll get f of x is 2,000 equals ab to the first power. All right, well, that makes things a little simpler because it just means that 2,000 equals ab, and we could choose to write this as 2,000 over b equals a. All right, now we're going to save that for substituting into the second one, 220, which means that x is 2, f of x is 20, and therefore 20 equals ab squared. But since we know that a can be rewritten as 2,000 over b, let's do that. Now here we got lucky. Because all this is telling me is that 20 is 2,000 b. So b is a very straightforward constant. What we have to do is divide by 2,000. 20 over 2,000 is 0.01. Okay, so very simply, b is 0.01. Or 1/100th. Now we can come back to the function we found here. 2,000 equals AB. Now with our knowledge that B is 0.10, this is saying that 2,000 is 8 times 0.10, 01, sorry. Now we multiply both sides by 100, and therefore 200,000 is A. Okay. Well, by the way, I just realized you can always double check these by plugging them back into the original function. But all right, so for this one, let's see, what do we end up with? So the function, very simply, ab to the x, we can rewrite it as f of x. A is 200,000 and b is 0.01. That's raised to the x power. Okay. So we're all set. That's it. So that one worked out well. That's because we got nice results. B is 0.01. It's not some scary radical. And then we plug that back into the first point and we're all set. Okay. And again, you can imagine what this is going to look like on a graph. It's just simply going to face up because A is positive. Oh, all right. Let's go look at it. There's no point in guessing. So we'll get rid of all of this. F of x this time equals 200,000 times 0.01 to the x power. Oh, it's going the, oh, that's why. You know why? Because B is a fraction. And you know why? It's still all positive, but it's facing down because B is a fraction. And what that means is that when x gets bigger, this ratio or this expression will get smaller. So, and by the way, here's where it cuts through the vertical axis, 0,200,000, which is what we'd expect because A is meant to represent the value of the function when x equals 0. So this works exactly the way we thought. Nice. That's always good when it works out the way you hoped. All right, hopefully with these, we'll get some nice answers too. So again, this is our starting point. And we're told that with -2,6, x is equal to -2, f of x is 6. Therefore, 6 equals ab to the -2 power. Now we have to watch it with this one because negative exponents are very confusing, at least potentially. So what we might want to do here is rewrite this. 6 equals a over b squared, because that's what it means. And then if you multiply both sides by b squared, you've got your answer for a. But again, just watch out with those negative exponents. Now here we have 3,1, which means that of course x equals 3, f of x is 1. And therefore, that means that 1 equals ab to the 3rd power. And we already have an expression for a. So let's take advantage of that. 1 equals 6b squared, b to the 3rd, which means that 1 equals 6b to the 5th power. Why is that? Because in the most general terms, just a quick reminder, so you're adding these two together to get that 5. Now, of course, this means that b is a very messy expression. Unfortunately, 1 over 6 is b to the 5th. And now, just like we did before, we can take the 5th root of both sides. So b is 1/6 raised to the 1/5 power, which is a constant. If you throw it into your calculator, you'll see that it's equal to, let's see. It's approximately equal to 0.7. All right. Now, we already know that A is 6 times B squared. We found that from above, so let's find that now. Since A equals 6B squared, we can now write this as 6 times, oh my God. So what are we supposed to do with this? All right, well, here's what we're gonna do. Here's the rule. We're gonna end up with 6 times 1/6 to the 2/5 power. Okay, the 1/6 doesn't change, the base stays the same. These two are multiplied together, the 2 and the 1/5. Wow, so we really got some messy numbers this time. Oh my God. So yeah, it's sometimes this is what happens with exponentials. So imagine plugging those back in now. Well, it's going to look messy, but you know what? That's exactly what it is. So therefore, so there's your A. In the brackets, I'll have the B, 1/6 to the 1/5 power, all raised to the X power. And believe it or not, that is your final answer. So just for the fun of it, I guess we can throw this into Symbolab because, I mean, it looks like it's going to be a catastrophe, but we'll find out. Let's try it. Let's see. They'll probably come back and say, sorry, that's too complicated. No, it won't do that. Hmm. 1/6 to the 2/5 power. And then we'll have 1/6 to the 1/5 power. And then the exponential here. All right, that should do it. Mm-hmm. Oh, I did something wrong. Sorry. There we go. I confused it for a minute there. That's bizarre. It's not offering me a graph. Oh no, there it is. Okay. Oh, all right. Well, you know, it's pretty much like what we've been seeing. And since B is a fraction, therefore it is going down, although it's completely positive. A is positive, and that means we'll never fall below the horizontal axis, but it is declining because as X goes up, this expression 1/6 to the 1/5 power is going down. All right, well, I think we deserve a simple one after all that. Hopefully this is the one. But you know, you have to be prepared for anything. And by the way, you can feel free to evaluate these. In other words, it turns out that this can also be rewritten as approximately 2.93 times 0.69 88 to the x power. Now that's only approximate. If you need the exact value, don't do that. But if you wrote that down on a test, that would be that would be fine, because that's roughly what this disaster equals. Okay, and you can see it's a lot simpler to follow that one. Okay, but it is only an approximation. All right, so that's why we might be reluctant to do it that way, unless, you know, we don't need that much precision. All right, so once again, we're looking for the function f of x is ab to the x power. And in the first case, this implies that x equals 3, f of x equals 1. 1 therefore equals ab to the third power. And I can choose to solve for either one of these. Let's go for 1 over b cubed is equal to a. Now for the second one, we have 5 comma 4, which implies that x equals 5 and f of x equals 4. So we have 4 equals a b to the 5th power. And of course, we know what a is from the previous step. So therefore, we have 4 equals 1 over b cubed. Now this looks very promising. I'll show you why, because this is the same thing as saying that 4 equals b to the 5th over b cubed. 4 equals b squared. Two is b. And therefore, since a is 1 over b cubed. Okay, so a equals 1/8. And so our final result (1/8) 2 to the x power. Yeah, like I said, we were entitled to a nice one. Oh, wait a minute. Uh-oh, let's double check that one. I want to make sure nothing went wrong. Hold on a second. X equals 3. F of x is 1. 1 equals ab to the 3rd, right? 1 over b cubed is a. Down here, 4 equals ab to the 5th. No, that looks pretty good. All right, anyway. Let's see what's next. Now, this next group is very straightforward because we're looking at interest rates. So we have a formula that we learned in the chapter for doing exactly this. A very straightforward formula. So let's go back to the chapter and grab this formula. This is the formula we'll be using to calculate the future value of an investment. And particularly if you put money in the bank, how much will it be worth in the future? Okay, so what variables do we have here? Well, first of all, P is the principal, the amount borrowed or lent. Well, A, all right, let's start with A, of course. A is the future value of a sum, which could be borrowed or lent. It doesn't really matter. R is the annual rate of interest. N is the compounding frequency, or number of times per year that interest is credited to our account. And then T is the time in years that the money is borrowed or lent. Okay, great. Now in this case, P is 10,250. Oh, I better split the screen so you can see what we're doing. There we go. 10 years. The rate is 4. The compounding frequency is 4. What is the future value of the sum? All right, so literally all we have to do is copy these numbers into this formula. All right, so we'll have 10,250. And then we'd have 1 plus 0.04 over 4. The exponent is 4 times 10. All right, now if you look at it carefully, you can see this can be very nicely simplified. 1 plus 0.04 over 4 is just 1.01, and that exponent is just 40. So let's see, let's multiply this out in our calculator. And that works out to be $15,260.85. So in other words, if you start out in your account with $10,250 and you left it there for 10 years, with this rate of interest, you'd end up with $15,260.85. Okay, so that was, compared to what we were just doing, that was pretty nice and straightforward. I think you'll agree. Now, what else were we supposed to do? Oh, okay. Now here in problem 6, you're supposed to redo this problem with monthly compounding. Okay, so in other words, nothing has changed except for n. N is now 12 instead of 4. So what I'm going to do is steal this formula and just change it a little. And let's see, so this 4 becomes a 12, and so does this one. Okay, now the question is then, what is the new value? So it's 10,250. If you divide 0.04 by 12, it's going to be 003333. We can round it a little. And then the exponent will now be 120. Let's see how much of a difference that makes. So 1.03333. 1.003333 raised to the 120 times 10,250 is 15,280.43. Compared to 260, yeah, so you can see it's a little bit more, it's almost $20 more. So when you're done with something like this, keep in mind, the more frequently the interest is compounded, the higher will be your future value. So when you get your answer, you should always have an idea of whether or not it looks right. And so here you can see that it's only slightly higher than the previous value, which is a good sign. Okay, so let me just double check something. Oh, you know what? I just realized I made a typo on my calculator. Well, actually, no, it got rounded. If you round it to that many places, that's what you'll get. Okay, so just keep in mind that here there's a lot of potential for rounding problems because this is not 4/12 is a third basically. And so you're going to have an infinite string of these threes. The more threes you leave in, the closer you'll get. The actual answer is almost $281, but this is close enough. Now, for this one, we're supposed to go back to the part, the chapter, problem 5, this original question. And this time we're going to change not the compounding frequency, but the length of time in which we leave the money in that account. Okay, in other words, we're going back to our original assumptions in part 5. And instead of changing the frequency, instead t becomes 20. Okay, now let's go grab the original formula. Well, I'm going to do that. And then I'm going to change t to 20. And we're going to find out how much of a difference that makes. All right, so this can be simplified to 1 raised to the 80th power. And then we have, all right. And that's going to be about 22,713. No, sorry, 721.33. So if you compare this one, let's split the screen here so you can see them side by side. The first case where we had 10 years, but still quarterly compounding, in other words, question 5, we ended up with $15,260.85. So it didn't double, but it did go up quite considerably. All right. So, all right, let's go on to the next one. Now here, oh, all right, well, this is very similar to the other two, except the compounding frequency. All right, well, let's try this one. Let me copy this formula. And fill in the numbers. So we were told that the deposit is 6,500, so that's P. The account is 3.6%. Compounding frequency is 2. T is 20 for 20 years. Okay, so how much will we have in 20 years if we put $6,500 in the bank and the interest is 3.6% per year, but it is compounded twice a year or semi-annually? All right, so let's plug it in. And let's see what happens. So 3.6%. N is 2 for semi-annual. Okay, and again, as always, this can be simplified a little. It's actually 6,500 times 1.018 raised to the 40th power. All right, and that works out to be, let's see, 1.018. $13,268.58. Okay. So those are pretty straightforward. I think you'll agree. But remember too that in the limit, we're starting to get into the exponential compounding growth. So that's why this is relevant to this section of the course. It's a nice, interesting application, especially because you may need this information down the road. All right, now for these are just straight ahead substitutions. Not that they're necessarily easy, but all you literally have to do is replace all the x's with -3s. Okay, so if you were to do that right here, now in principle, I guess you could leave it like that, but why don't we figure out the actual value? Because keep in mind what this means is 2/5 cubed, which is 2/125. Now, again, you can leave it like this, or if you want to calculate the actual decimal equivalent, it's 0.016. So this is okay, this is okay. Even this is really okay. But, you know, it depends on what you're trying to do with this information. If you're trying to solve for a specific problem, you will eventually need that 0.016. All right, now for this one, keep in mind too with these, all you really have to do is be careful. So we have -4. Now, up here in the exponent, we have -2 plus 3. So you've got -4 to the first, or just -4. Well, that was nice and easy. We like that one. Now for this next one, well, look how easy this one is. F of 3 z cubed. And if you plug that into your calculator, e cubed is approximately 20.0855. That's it, you're done. And then here you have f of -1 equals -2e to the -1 minus 1. And so keep in mind, this is the equivalent of -2/e squared. And should you plug that into your calculator, e squared is approximately equal to 7.389. And so you're going to get roughly -0.27. Okay, about -0.27. All right, let me just leave it there for a minute so you can catch up. The next one is a growth problem. We did a few of these in the slides. And so what I'm going to do is scroll back to the chapter so you can see what this refers to. All right, so somewhere in here, we have this formula where we are dealing with growth rates. Maybe it was further back. We had the example of, here it is, the deer. Okay, so this is what we're using. I mean, the notation isn't really that big of a deal. It's kind of useful to have it rewritten this way to remind ourselves that time is involved. With an exponential function, it isn't necessarily true that time is involved, but here it is. So what do we know in this problem? Well, first of all, t is time, and n of t is the number of, in this case, foxes at time t. And then, of course, a is the initial value, or the initial number of foxes, which, by the way, means this: n of 0 equals a. That's what we're saying here. The initial value, n of 0, means the number of foxes at time t, time 0 rather, is a. And then b is 1 plus the growth rate of foxes. Okay, now here they're asking us for the predicted population in 2020. Now this is the challenging part. The years must be converted so that in this case, the first year is t equals 0. Okay, so in other words, we always want to start at 0. So in this case, 2012 will represent t equals 0. Okay, because that's the starting point. Therefore, 2020 represents t equals 8 years later. Okay, so we have to be careful that if you plug in these actual years, you will not get the right answer. The formula was based on the assumption that you have replaced the years with time. So be careful with that. Okay, so once we got through those hurdles, let's do this. So what have we been told? Well, let's see. The growth rate is 9%. Okay, so since the growth rate is 9%, or 0.09, equals 1.09. Okay, so remember, b is actually 1 plus the growth rate. The initial number of foxes is 2012. So n of 0, which is the same thing as a, is 23,900. What else do we know? We're looking for the predicted population in 2020. Okay, so we are looking for n of 8 because this represents the number of foxes in 2020. So let's plug in some numbers. So if this is our original function, we know the values of a and b. We can replace this with 23,900 times 1.09 to the t power. And then we can solve for any year we want. See, that's the great thing about writing it like this. This function can be found or used to find the fox population in any year. But since we're specifically interested in 2020, t equals 8, so that n of 8 equals 23,900 times 1.09 to the 8th power. And when you plug all that into your calculator, you should get, let's see, 47,622.25. Which now, by the way, because the foxes have to be an integer, this is rounded to 47,622. In other words, in this case, you do not want a fractional part because you can't have a fraction of a fox, obviously. Very good. All right. So these are pretty straightforward too, as long as you remember about this part with the time. Okay, that's an important detail. Yes, that's a very important detail. Now, now here's another one. It's very similar, except that you're solving for B this time. Now, how do I know that? Because it asks for the annual growth rate. So first things first, we know that 1985 will become t equals 0, because that's where we know the value of the house. So we're being told n of 0, the initial value is 110, which in turn equals A. Actually, let me write it like this. Now B is what we're looking for. 2005 is t equals 20. And we're told that n of 20 is 145,000. So what we're going to do is solve for B. The growth rate will be B minus 1, since B is the growth rate plus 1. All right, so how do we set this thing up? 145,000. Well, actually, let's do it like this. N of t, we'll write the general form, is 110,000. Well, this is not that helpful, is it? So let's do some substitutions here. N of 20 is 145,000, which in turn equals 110,000 times b to the 20th power. Okay, so this is what we're actually working with right here. So we're going to divide up both sides by the 110,000. Actually, I might as well just do the division directly. 145,000 over 110,000 is 1.31818. Let's say, is b to the 20th power. So you might think, what are we going to do now? Well, here's what we have to do. We're going to take and raise both sides to the 1/20th power. So the exponent here is 1 over 20. Okay, because b to the 20th power raised to the 1 over 20 equals b to the 20 times 1 over 20, which is just b. So basically, all we have to do is solve in our calculators for 1.31818 raised to the 1/20th power. And that works out to be approximately 1.0139. Now, remember, we did say we're looking for the growth rate. So since B is the growth rate plus 1, the growth rate is B minus 1. So in other words, the growth rate is B minus 1, 1.0139 equals 0.0139, 1.39%. All right, so in other words, in order for the house to be worth this much money in 20 years, the growth rate every year must have been 1.39%. Very good. All right. Now, referring to chapter or problem 14, what would be the predicted house value in 2010? Well, the way we set this thing up, 2010 would be year 25. All right, so let's copy some of this information again. So since T, 2010 would mean that T is 25, because remember, 1985 was considered to be year 0. Now, we already know from up here that, well, actually, we can replace this B now with 1.0139. So as we previously knew that A was 110,000, we've just gotten through proving that B is 1.0139. So A is 110,000, the value of the house in 1985. B is 1.0139 from problem 14. So now this is our general expression, and we can just now go in and say, well, you know what, we want to know what it is in 2010. Now, of course, you notice we're assuming that that's in the future, which is, of course, not the case. But at the point in time that we were doing this analysis, that would have been 5 years in the future. Okay, so therefore, 5 years from now, the house will jump up again if the growth rate continues, of course, which is what we're assuming. So it'll go up to 155,000. 335.52. Okay, so in other words, it went up to 145,000 in 2005. And now if we keep the house for 5 more years, it should be worth 155,335.52 cents. All right. Now, this next one is very interesting because it's the same exact kind of problem, except for one little detail. The growth rate is negative. Okay, so in this case, the growth rate is negative, which means B will be less than 1. All right, the question is how negative? So let's figure some things out here. First of all, 2007 means that T equals 0. 2013 means that T equals 6. 2017 means that T equals 10. All right, that has to come first. Now, the basic formula, of course, is this. And we're told a couple of things. The initial value was 38,000. The value in year 6 is $11,000. All right, so let's start with this general expression and replace the A with 38,000. How do we find B? We can do the following. N of 6 is 11,000, which means that we have 38,000 times B raised to the 6th power. Okay. Now, how do we solve that? Well, let's divide both sides by 38,000. So 11,000 divided by 38,000 is about 0.2895. B to the 6th power. Now we know the trick now, what to do next. We're going to raise both sides to the 1/6 power. So here I raise this to the 1/6 power, and therefore that gives me just plain B on the right-hand side. Because remember, okay, and so if you take out your calculator, 0.2985 raised to the 1/6 power is approximately 0.8175. Okay, now here's a little note. This implies that the growth rate is 0.8175 minus 1, which is negative 0.1825. So in other words, this means that the car is depreciating, although it didn't ask us for this, at a rate of 18.25% per year. Okay, I just thought I'd throw that in there for you so you can see what's going on here. Now, with all that being said, remember what we're looking for. We want to know what the car will be worth in 2017, which is year 10. All right, so what do we know? Well, we figured out earlier that we had this. Once we figured out what B is, we can simply replace that right here. 0.8175 is now the official general formula. Okay, where we found the B up here. The A we already knew was 38,000 because that was the initial purchase price. So to find N of 10, all we have to do is replace that T with a 10. And when you do that, you're going to have $5,000, approximately, of course, 65.95, let's say. So that's how much the car should be worth at that time. All right, so that's how that one works. Now, let's see, what else did we have? Was that the last one? Looks that way. All right. So there were 16 questions in part 1. Now, part 2 is the one that I accidentally forgot to post, it looks like. But I'd like to go over that anyway so that we can get back into the trigonometry. It's just exactly what we were doing last week. So let me go get it open. And so as usual, I'll post the solutions to this one on Moodle. And now let's look at number 2. Here we go. All right. All of these have something to do with logs. Now, of course, this is something that we could all use some help with. Now, these look very abstract, and of course they are. But once you get some practice, they'll start to become second nature. All right, so, logs are something that you either see them on a regular basis or you don't. Certain disciplines use them all the time. Some of them hardly ever use them. So what exactly is going on here? What they're asking you to do is say, let's rewrite this as an equivalent exponent. In other words, this expression implies that 4 raised to the m power, whatever that is, equals q. Why? Because that's the definition of logarithms. So these two statements mean the same thing. 4 to the m power. Now, if you can't remember, use a straightforward example. Like this one, for example. Let's say you were interested in the log to base 10 of 1,000. This equals 3 because 10 to the 3rd power is 1,000. So with that as your basic starting point, you shouldn't have any trouble with these other ones, even though they're very abstract. Like I said, they're letters. It's much harder to deal with letters than to deal with numbers. Okay. Well, then in that case, let's try this one. So if you have an actual numerical example in front of you that makes sense, you should be able to reason it out. So here, for example, based on the same reasoning, a to the c power equals b. And it's always the same. In other words, if you look here, you'll notice that this a becomes the base of the exponent. And c is the exponent. And then b is this constant. And it's always the same. All right, now how about this one? This one is telling me that 16 raised to the x power is equal to y. And then finally, this one is telling me that x to the y power equals 64. All right, so those aren't that hard. Now here we're going the other direction, okay? So this one might be a little trickier, but just bear in mind. So the base, this is the base of your log. And this y is what you're taking the log of. So again, if you're not sure, just imagine you encountered the following. 10 cubed equals 1,000 is the same thing as saying log base 10 of 1,000 is 3. Okay, so you're taking your, this is your base in the log. The 3 is your actual answer. and you're taking the log of y. And it's always the same. Okay. So if that's the case, then this next one is straightforward. Log base 10 of b equals a. Now, how about this one? Log. Now this one is a little different because, well, you'll see in a second. Log base e is the natural log. All right, and then one more. Trying to find some space here. Yeah, all right, I'll write it right here. Log base 19. Oops. Okay, log base 19 of y equals x. All right, now we can deal with some actual numbers. These are, like I said, these are very abstract. This is just to quickly remind you how this function and this function are the same thing. Or this, I shouldn't say function, equation. But now we're going to get to the point where we're actually solving. All right, so in other words, in these cases, there's an x in there, and we're trying to figure out what its actual value is. So just keep in mind that in these cases, you can rewrite this based on the definitions of logarithms. This one, for example, implies that 3 squared is x, which of course is the same thing as saying that 9 equals x. Okay, and you can double check it if you want. 9 equals x. The log base 3 of 9 is 2. You don't have to always do this, but log base 3 of 9 equals 2 because 3 squared is 9. All right, well then what about this one? 2 to the minus 3rd power is x. Now remember what that means. 2 to the minus 3rd is 1 over 2 cubed equals x, which means that 1 over 8 equals x. Okay. Now here, this one tells me that 5 squared is x, or very simply, whoops, 25 is x. And then finally, one more, 3 cubed is x, 27 is x. And that's it. That's all you had to do. All right. Now, simplification. Now, by the way, I do want to point out here, that I took some of these out of the textbook. I was just thinking that, strangely enough, they chose not to have a base in any, some of them are natural logs. The reason why they left off the base is because the base is actually irrelevant in these cases. In other words, like if you look at the first one, it doesn't matter if this is base 2, 10, whatever, the rules are the same. And so what they're trying to establish here is this. And by the way, there's more than one way of doing this. But if you can do the following, one of the rules we learned is that the log of xy equals the log of x plus the log of y. And that cuts both ways, of course. So we have the sum. So what we can actually do here is rewrite this as the log of 2x to the fourth times 3x to the fifth which is a log of 6x to the 10th. Oh, sorry, 9. What am I saying? 10. 9. Okay. Because what I'm actually doing here is adding the exponents. Now, there's one more step we can take based on this property, which I'll remind you of. In fact, let's sneak this over here. The log of x to the a power equals a times log of x. Okay, so these are two reminders. So let's put these over here. So in other words, by multiplying these together, 2x to the fourth, 3x to the fifth, I have 6x to the ninth. If I want to, it's not absolutely necessary. I can rewrite this as 9 log of 6x, and I'm done. Okay, so, and again, the book left off the base just to remind us that these properties actually hold. Now, it is understood, of course, that these are the same base. In other words, whatever those two logs are, they have to have the same base. It could be 3 or 2 or 8 or whatever. As long as that part is understood, it doesn't actually matter what the base is. So that's why they like to write it like this. I guess it's a little bit simpler. But yes, it does have to be the same base. But if it is, we don't necessarily need to specify what it is. So we end up, after all that, with 9 log 6x. All right, now this next one, clearly, like I said, log written as ln is log of AC. And so you might recall, well, here's another recall. Let me sneak it into this list here. Log x over y is log x minus log y. So this one can be rewritten as natural log six x to the ninth over 3x squared. Now, once we get it to this point, we can often simplify it. 6 over 3 is clearly 2. X to the 9 over 2 is 7. Okay. X, just a quick reminder. That's why this is happening. And then, of course, you can rewrite this as 7 natural log of 2x. All right. So the properties above are the ones that are letting us do this. And you know, in some cases, this can make a big difference in, as far as how simple these results really are. Okay, let's see. Now, something like this, you may have to work it backwards. But keep in mind, you can always do these in multiple ways. So sometimes the strategy is maybe not as clear cut as you might think. Let's try this. This is equivalent to saying log of x squared plus log of x plus 1 cubed. And since it's a sum, it's log x squared times x plus 1 cubed. And I think that's as simple as it's going to get. Yeah, that's it. We can't take it much further. And even then, it's kind of up in the air whether or not this is really simpler, but that's one way we can approach this. Now, what about this one? What's going on here? Well, this one's kind of interesting. We can start by rewriting it as log x and then this one can be written as minus log y to the 1/2 power, or 0.5. I'll leave it like that. Plus 3 log z cubed. Actually, let me write it like this. Okay, well then we've got log x. Because these two are being added together, I can turn that into a product. And since I'm subtracting this one, I can write that as a ratio. So I'm basically reversing these two rules right here. The two that are added go in the numerator. The one that's being subtracted goes in the denominator. All right, so that one was a little tricky, but we did it. All right, now we're going to have some interesting cases here. What do we do about this one? 9 to the x minus 10 power equals 1. Now, what do we do about this? Now, whenever an exponent shows up, or sorry, the variable x shows up in the exponent, the first thing you want to think is, can I use logs to simplify this? And the answer is yes. All right, so in other words, what I'm about to do is just take the log, but I'm taking a specific log. I'm taking the log of base 9 of both sides of the equation. Now, here's an important detail. Why did I choose log 9? Because let's remember, if I have log, let's turn this into a recall. The log to base a of a to the x is simply x. Okay, as an example, the natural log of e to the x is just x. the log base 10 of 10 cubed is just 3. Because it's the same thing as saying the log to base 10 of 1,000 is 3. So by taking the log base 9 of both sides, what I can do is simplify the expression on the left to x minus 10. On the right-hand side, I have the log base 9 of 1. But this happens to be a very simple case. You might remember the log to any base of 1 is just 0. So what I've got here is that x minus 10 equals 0 or x equals 10. And in this case, I think it might be a good move to do a double check. Nine to the x minus 10 equals 1. If we plug in 10, oh yeah, it works. Perfect. So the trick is to choose the right logarithm to take on both sides of the equation. It has to be the same, of course, otherwise it'll affect the results. So what you're basically trying to do is figure out how to simplify it as much as possible. So I chose log base 9. All right, so does that make sense, everyone? Once you catch on to that part, the rest is just straightforward. It's just based on the definition of logarithms that we've been studying. All right, so let's try B. Well, now I think you're getting the idea. Now remember, this is e to the x, all right? So here's what we're going to do. We're going to take the natural log of both sides of this equation. And by doing so, we'll not change anything. All right, so here we may need to do a little rearranging. So for example, what if I divide both sides by 2? Well, actually, no, I can't. No, I'll tell you what, let's do that first, just to keep it a little simpler. E to the 6x equals 13/2. Okay, so if that's the case, you'll see why I'm doing this in a second. All right, I'll tell you what, let me. Hold on one second. I'm going to do this by hand. Anytime there's fractions involved, it starts to get very messy. So I'm going to do it by hand. So e to the 6x could be rewritten as 13/2. Now let's apply the logs. Now, if you recall, the natural log of e to the x equals x. So therefore, the natural log of e to the 6x simply equals 6x. So 6x equals the log of 13/2. And then now we're done because we just have x equals 1/6 of log 13 halves. All right, very good. Now let's go on to the next one. And again, we see that there is an e to the x here, which implies that we'll almost certainly want to use natural logs. But first, let's clean it up a little bit. Make it so much simpler. So we add 8 to both sides. And we'll end up with negative 54. Now let's divide out by that negative 5. All right, so we've got e to the 9x minus 8 is 54/5. So now we're going to take the log of both sides, natural log, I mean. And that means that 9x minus 8 is the log of 54/5, which means that 9x equals log 54/5 plus 8. And then finally, I can just divide by 9. Okay. And that's it. All right, now let's do another one. Now, again, let's try to simplify it as much as we can. Let's start by subtracting this 2. And then we'll divide by the 10. Of course, we can simplify that. Now we find we can apply the natural logs. And so we end up with, whoops. Okay. And then I subtract the 3. And then finally, I just divide out by the 8. Oh, it was a mess, but it worked. That's the number. That's what matters. Now, of course, this is equal to some constant or other. If you needed this for some problem you're working on, you could easily do the calculations to turn it into a number. In fact, I'm going to do that right now, just because you may want to know the log of 3/5 minus 3 divided by 8. It's approximately minus 0.44, if you're wondering. But we can just leave it like this. Well, let's do another one. So we'll add 7 to both sides in this case. Divide out the 4. So this one's really straightforward, and then take the natural logs. Subtract the 3. And then divide by 3. That's it. That's all we needed. Very good. All right, now we got some solving to do. We're basically just using the same properties. This time we're looking for a specific value. Well, it's the same thing we've been doing, except that here we're taking the log of both sides. In these cases we've already got logs. We may have to do something different. So here, for example, and what I mean is you may have to use the definitions of logs to get to the answer you're looking for. Like here, for example, this is the same thing as log 7 is 2. Now remember, log, let's use this. This is my favorite example because it's easy. So with that over there, you can see that this is equivalent to saying that 7 squared is x. Or 49 is x. Because over here, remember, what we're saying is that 10 to the 3rd power equals 1,000. So you start with the base, and here's your exponent. This is what you're solving for. So in other words, this implies that x is 49. Okay. So just based on the definition of logarithms, you're taking your base, you're raising it to the 2nd power and setting it equal to this value, x. All right, now how about this one? Let's see, first let's divide up both sides by -8, which means you have -2. And then that implies that 9 to the -2 power equals x. And 9 to the -2 power is the same as 1 over 9 squared, or 1 over 81. Okay. Let's try the next one. Now here again, we've got to do a little algebra. So I'll obviously subtract 4 from both sides. And this tells me that 2 to the minus 2 power is 9x by the definition. All right, now this step is always just by definition, which is 1 over 2 squared, or 1 over 4. Now I'm going to divide both sides by 9. And I'm left with 1 over 36. And that's our final answer. All right, let's try another one. So we'll do a little algebra first, and then we'll apply the definition of logs. So let's see, we subtract the 6. Divide out the 2. And then this implies that 2 squared, or 2 raised to the 2nd power, equals 8x plus 4. And then this just means that 4 equals 8x plus 4. And then 0 equals 8x. And then x is 0. All right. Now there's more, there's a few more, but I think it's definitely break time right now. So we got 2 more batches of these. We'll save these. We'll have our usual break. I think we've all had enough for now. We'll go through and finish these up, and then we can get back to trig functions. Now, I did say there's 1 or 2 videos, but I'm saving them until we've reached a certain point in the discussion, because otherwise they won't make any sense. So we'll dive back into what we were doing last week and revisit our trig functions. And if we get far enough, I can show you these videos that help us understand how trig functions really work. But so we'll finish this up. This is the chapter 4 problem set. And then we can focus our attention on trigonometry for at least a while. When that's done, the next topic after this is completely different. It involves probability theory and statistics, which is a very applied part of math. And we can do a lot of very interesting things with it. But first, we want to make sure that we're pretty good at trig before we go on to that. All right. So like I said, you'll need that for Calc 1, or you might run into it again in another course. So anyway, let's stop for a bit, as we always do, 15, 20 minutes. And then when we come back, we'll be ready to finish these up, and then we'll dive back into trigonometry. All right.
Excuse me.
Yes.
I was wondering, were you able to get my midterm?
Get it? You mean to correct it?
Well, yeah.
No, they're not done yet. Sorry.
No, I'm not expecting it, but I was just wondering, because I emailed you saying I had trouble, you know what I mean? And I was just wondering if you, I was just wondering if you just like received it in the first place.
Okay, yeah, no, go ahead. You know what you do, but send me another email today, and I'll as soon as I see it, I'll go look into it.
Okay. Okay.
Gotta be careful, but I'll look specifically for yours to make sure that it's there. Okay.
Yeah. I'll give you another email just to
yes.
refresh the page and try to go up on top.
The chances of me finding it now are pretty low because I get so many emails. If you send me a new one, I'll double check it right away.
Yeah, well, hold on.
Okay, so then as far as the correcting goes, it'll probably have to take until the weekend because there's,
No rush. Hey, as long as you get it, that's the main
right, I
point.
know,
You know what I
I
mean?
know. It's just that I got all three of my classes here, had their midterms at the exact same time. It's a little overwhelming sometimes, but it'll get done soon enough. But yeah, just send me an email and I'll double check it specifically for yours. Because you're right, the technology sometimes doesn't work that well, and sometimes the files can get too big.
Honestly, I don't know. Like, it was weird for me, my situation, because like it did not. If the file is big, it will say the file's too big. You can't send this. You know what I
Right.
mean? But it was letting me send, so it
Yeah,
couldn't be too big. And
You
then
know
like,
what?
but it wouldn't send though.
I,
That was-
you know, now that you mention it, I remember this case now. I'm pretty sure it's there. I'll just go look right now. Yeah, because it's ringing a bell now. Let's go look, because I'm pretty confident I remember seeing that one. That one in particular. And you know, if it didn't come through, you could always send it again. But I'm thinking, now that I'm thinking about it, I do recognize that. Let's go get that. Watch this. And one of these, yeah, this
Yeah, emailed you. Mine's just
the whole, is this the whole thing right here?
yes,
Oh, it's this one. Oh, how could I forget this one? Yes.
yeah, that's the notes part. But I was wondering, if you have the midterm part, the MAT.
This isn't it?
No. Those are the notes part. It's still part of the midterm. You know that where you're going to check to correct my grades. I mean to correct my question. You know, see how I came upon the problem. But I hold on.
I don't understand. What is got there are we looking at here? Is this your test or not?
No. Those are the notes part. Meaning
I don't know. I don't know. I don't understand what you mean by that. The notes part.
How those are how like I wrote the I numbered the question, and then what I did was that's still part of the midterm where that's my check my work part, you know, where I solved it myself to
Right.
you know.
Well, then what's missing? It looks like it's all there to me. It looks fine.
Hold on.
Did you write the answer separately or something?
Yes, that's what I'm trying to say.
But are these the answer? There's, if it's circled in red, is that your final answer? If that's the
Yeah.
case, that's all I need.
No. But there's more but there's a section where I did half on this part. I did most on this part and a little bit on the test because there's enough space. You know what I mean? Where
Oh, well, all right. Well, ideally, you should not do that. It should all be one or the other. But so you're saying that there's a part that you did on the physical exam, which is still not here.
yeah.
All right. Well, that part, I don't know where it is.
I don't know how like you don't have it when it says on my end that it's sent, but I'll try to send it
Oh
again.
no, you should never assume the technology is this. I don't know what this is. Is it possible that this is it? Did you turn it into a PNG file?
That's not what it said on my end, but hold on.
Well, just here's what you do. Just send it again. Because
Okay, I'm sorry.
you know what? No, you can't ever assume the technology works correctly, ever. It doesn't matter how simple it is. So just resend it.
And I tried to email you, you know, to say, hey, reach back, and you didn't say anything. So it's like I
Well, I
wasn't trying
thought
to
this was
fix-
what because that's what I thought this was it. You're all set. I mean, it looks like it at first glance that it's all there. But if there's more, then just send it right now.
Okay.
By the way, I wondered, like, now, what exactly did you do to get it like this?
I used my notes app on my iPad because what I wanted to do is like I want to show my work. I didn't want to like just write my
No,
work all on
absolutely. No, it's
all
just
the
that I was
answers on
wondering.
tests and you know you're thinking, wait, so is this kid going to explain how he like came up with this answer, or someone just wrote it for him? You know what I mean?
No. This is exactly what you wanted. No, but I've never seen this format before. You said it's notes on iPad.
Yeah, and
It comes with it. Or did you have to buy this?
no, it came with it.
Okay. No, the reason why I'm asking is because I want to, in the future, I might recommend that people try this if they have an iPad, which many people do, because it looks nice. It might be bulky though, but still, look how nicely it turned out. It might be easier than writing it by hand and then taking a photograph of it. So I will try to remember that this option is on the table. So, but anyway, if there's something missing, just go ahead and send it right now.
Yeah, that's
yes,
what I'm
it
trying to do.
does. It does look like Khan Academy. Then that must be what he's doing. I never thought to ask or try to find out. Apparently, Khan is just writing on an iPad when he's doing his lectures, because this is exactly what it looks like. It's kind of cool.
Thank you.
I like it. All right. Well, anyway, so if you think there's something missing, just go ahead and resend it. We'll
Okay.
get this straightened out. This is the rest of it, though. For that part, you should just take pictures, I guess.
Yeah, what I'm going to do is I'm just going to screenshot it then at this point.
Yeah,
because
exactly.
the file itself won't send, and I have no idea
No,
why.
if it's too big, it's probably too big. Just do one page at a time.
Okay, yeah, that's what I'm going to do. I'm sorry.
That's all right. That should take care of it. I know this happens every single semester. There's always a few people where the email simply won't cooperate. Like I said, it's not as reliable as people generally think it is. And so this is a classic example of that. It just refuses to work. So yeah, so give it another shot, but this time try to do just one page at a time and see what happens.
Yeah, I'm going to do that. I'm definitely going to do that.
All right. So then I guess other than that, I guess we're all set. So we'll just have our break now. And then when we get back, we'll wrap up this chapter 4 problem set. And then, of course, carry on with trigonometry. Okay. Very good. All right, let's wrap up these last two sets, and then we can go on. Like I said, we need to get back into chapter 5, which is our overview of trigonometry. And so we'll just quickly use our properties of natural logs and other logs to take care of these. Now, you might remember somewhere in the chapter 4, let's go find it. There is a property that tells us, it would have been the second part of the chapter. Hold on. 4, no, it's all one. Okay. It's all, let's see. Here it is. For any real number, so we know that if you have exponents with a common base, like for example, if you had something like this, there's a base of 2, and the exponents are x minus 1 and 2x minus 4, you can just set them equal to each other. Now, the reason why that's happening here, and we didn't mention this earlier, is because what you're really doing here is taking the log to base 2 of both sides. And that's what reduces it to this. Okay, but you'll have something similar with logs. Let's see, we did something like this. Here it is. If you have 2 logs with the same base, that implies that in this example, s equals t. Okay, and it's for the similar reasoning. You're basically raising both sides to the b power to do this. But so here, if you look at this very carefully, log 10 minus 3x equals log negative 4x. Because these are the same log, meaning the same base, all you have to do is rewrite this as 10 minus 3x equals negative 4x, and then solve algebraically. And of course, if you're not sure, you can easily double check. In this case, you would plug in the negative 10 and see if these are in fact equal to each other. And you're right. I mean, it works. So the double check is correct. So negative 10 is the value of x. And again, the reason is because both of these are the same base. So in other words, what you're essentially doing here is saying, if you had the log 10 minus 3x set equal to the log of negative 4x, what I can actually do here is apply this e function to both sides. And if you recall, e to the natural log of x equals x. So therefore, what I have here is that 10 minus 3x equals minus 4x. So in other words, this is the reason why you can do this. All right, but all you have to remember is that as long as the base is the same for both logs, you can just set what's inside the parentheses equal to each other and solve for x. You don't have to prove why this is happening. All right, so like for this one, same thing, exactly the same. What you're gonna do is say, all right, well, these are both natural logs, therefore, minus 3x equals x squared minus 6x. And then what you can do is probably what we should do is gather everything up on the same side. So let's say add 3x to both sides, 0 equals x squared minus 3x. And then I can rewrite this as x times x minus 3. So this one actually has two solutions, x equals 0 and x equals 3. Okay, so, and if you double check, you can double check them each individually, and you'll see that both of these do in fact satisfy this equation. But this time there happen to be two values of x that both satisfy this equation. Now here, again, we have the same scenario. Even though it's not natural log, it's log 10. That's all that it takes for us to conclude that we can just write this as x plus 3 minus x equals 74. So there, oh, wait a minute. You know what? I just remembered I was supposed to delete this one. This one is not, this is not a valid question, because if you can see, you're just going to end up with 3 equals 74. So make a note somewhere that this one is not going to work. So we'll just dispose of this question. It was not set up properly, so we can't solve for it, unfortunately. So let's just pretend we never saw this one, okay? And then for this one, we have the same thing. Base is 4 for both logs. 6 minus x equals 3x. 6 equals 4x. And then finally, 6 over 4 equals x, which is the same thing as 3 halves. Perfect. All right, now here we're going to have something similar. Well, actually, oh, this is very strange. This is, wow, this is kind of interesting, because it just says, oh my God. Well, you know what? Let's dispose of this one as well. This is just the definition, so we won't count that one. Oh man. All right, let's try this one. Now this one, what we're going to do is we're actually going to use the definition of logs. All right, so again, if you've forgotten, remember our favorite example. So what I'm going to do is rewrite this as 2 cubed is 7x plus 6. Okay, and so therefore 8 equals 7x plus 6. 2 is 7x. And then finally 2/7 is the final answer. All right, it looks like there's only one more. So this one, with all the same base, implies that x plus 6. Oh, see, here's another one. This is an example of bad planning. Yeah, this one didn't work out, sorry. So let's just toss this one as well. So yes, I'll make sure this doesn't happen on any of the tests, that's for sure. So I have to be a little more careful when I plan these. All right, so there's 2 or 3 of these that do not work, so let's just pretend they don't exist. And yeah, so we're done then. That's it. We're completely done with this section. So now we can get back at long last to our discussion about trigonometry, which may not be anyone's favorite topic, but at least we know that it can be very important for certain applications. So, all right. So as usual, like I said, I'll post these on the Moodle. The ones that are in red are the ones that are not correct. Okay. In other words, you can't solve those. So the rest of them are fine, and all the answers are here. All the details are here, step by step. It's a big document. Man, look at, oh, and this is just part 2. I forgot about that. Part 1, it looks like I saved it already. So I'll put both of these. In fact, you know what? Let me just do it right now. This will only take a minute. That way, I eliminate the risk Oh, this one is not labeled correctly. Yeah, hold on a second. That's better. Okay, so let me just quickly put them in Moodle as long as we're here. It reduces the risk of forgetting about it. That's what it does. Okay, so all right, so that's taken care of. That's 4. All right, so let's get back to where we were with 5. We actually started to go over this, but I know that we didn't finish it. There's still a long ways to go. And we started to work out some examples just to refresh your memories, which is important because I know you've seen some of this stuff before, but it's probably been a while. And so we'll go through this and we'll review a little bit, and then we'll introduce some new ideas. First, let me quickly save this. This is chapter 5. But today's the 27th. All right. So remember now, these are the basic 6 trigonometric functions. And you, after a while, you're so used to seeing the abbreviations, you forget that they actually have full of spellings. Like sine, for example, is actually S-I-N-E, but we frequently abbreviate it S-I-N. Same thing with cosine, tangent. We have cotangent, secant, and cosecant. The first 3 are the ones that you can remember with the mnemonic device that we all know and love, SOHCAHTOA, which I put in here somewhere. SOHCAHTOA. And that helps remind us that the sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. The other 3 that we saw are derived directly from these first 3. In other words, cosecant is the inverse of sine, secant is the inverse of cosine, and cotangent, as the name suggests, is the inverse of the tangent. Okay, so you can figure out any of these. And so we will often apply these to right triangles, but it doesn't have to be a right triangle. And so we did some examples here where, for example, we figured out the sine of 30. 30 is this one down here in the bottom right-hand corner. The opposite is 1. The hypotenuse is radical 3. And then, of course, as is so often the case, when we have a radical in the denominator, we'll simplify it by multiplying by, in this case, radical 3 over radical 3. So this would normally be listed as radical 3 over 3. Now, often textbooks have tables that will enable you to, at least it'll show the most important ones. And this book is no exception. Somewhere in that book, there is a table of these trig functions. In fact, you know what, maybe we can find one on the internet. Oh, they're all over the place. Like this one. No, I don't like that one. Let's do, this one's kind of nice. And so what I'm saying is that, you know, if you've got this nice table in front of you, it certainly makes things a lot easier. And so for sine, we can confirm that the sine of 30. Oh, wait, what happened here? They've got something else there. Oh, hold on. Let's see. You know what? I'm wondering if our calculators have this. I know everyone has access to the iPhone. You probably have a nicer calculator than that too. I don't know if these iPhones have trig. Oh yeah, they do. Let's see what happened here. OH, yeah. All right, you know what I just noticed? Your iPhone does have a scientific calculator built into it. And if you turn it on its side, if you get the calculator app and turn it on its side, you'll see it is a scientific calculator. If you look in the bottom left-hand corner, it has sine, cosine, and tangent. I'm not sure if it's set up for radians or not. So let's see. Yeah, I must have drawn this picture incorrectly. Oh, I know it went wrong. I labeled this thing. Ugh. All right, well, let's fix this right now. I had these two backwards, that's why. This should have been the 2. You know how you can tell, because with the Pythagorean theorem, it should be 1 squared plus radical 3 squared is 2 squared. 1 plus 3 equals 4. 4 equals 4. Sorry about that. So this one should have been not 1 over radical 3, but 1 over 2. Okay, that means this one's not going to be right either. All right, so it's 1 over 2, which is very nice and easy. And then the cosine, let's get this out of here. Of let's say 30. So from 30, adjacent is radical 3. That would be radical 3 over 2. Now, if you go to your calculator then and hit the sine button, what you're going to do is hit sine and then 30. It appears now that it is set up for degrees rather than radians. I don't know how it handles radians, but it looks like it's already designed to do degrees. So you hit 30 and then the sine button. So on the calculator, and if you have a more advanced calculator, you might be able to do this in a different way, but at least on the iPhone calculator, since I know you'll have one, you might as well learn it. You would hit 30 followed by the sine button. You actually don't even need the equal button. It goes right to 0.5. Just 30 and sine, and the answer turns out to be 0.5. Now, here's one of the awkward parts, though. What if you want cosine of 30 instead of sine? Now, we know already that it's radical 3 over 2. And this table agrees with me on this one, radical 3 over 2. The problem is that when you type it into your calculator, it's not capable, or at least I don't think it is, of showing you the radicals. It's going to give you the actual value. So let's try that as an experiment. So 30 cosine, yeah, 0.866. So what you have to do is recognize that if you go back to your calculator and type radical 3 divided by 2, you will in fact get 0.866. So I don't know if there's anything we can do about that. I mean, the calculator isn't that sophisticated. For something like that, you need a much more high-powered scientific calculator. But it's there if you need it. Okay, just in case you want to double check your results. So what you could do is say, well, is radical 3 over 2 equal to 0.866? And you discover that, yes, it is. And while we're on the subject, let's do the tangent. Opposite over adjacent. Now, this is the one that we thought the sign was. It's 1 over radical 3 over radical 3. So if you type that into your calculator, tangent 30, let's try that. 30 tangent comes back with 0.57735. And if you double check, the square root of 3 over 3 is in fact 0.57735. Okay, so the calculator can help you up to a point, but you just have to be careful with it. And then, of course, you could do the same thing with 60. You could do the same thing with 90. Just be aware, though, that for some values, the tangent is undefined. According to this chart, the tangent of 90 is undefined. All right. So anyway, now we reminded ourselves exactly what it means, what an angle actually means. It means that it's essentially telling us that if we had two rays, the angle between them is the rotation that's needed to move from one to the other. That's how it's described, rotation. And when they say rotation, they mean with respect to a full 360-degree circle. And in the sense that 1 degree simply means 360th of an entire circle. Okay, so 60 degrees means 1/6 of the way around a circle. Now, this base 60 is kind of annoying, but it was invented by the Babylonians, and I guess they must have done a lot of work in this area. So we've been using base 60 for our geometry ever since. It would have been nice if it was based on 100, but it didn't work out that way. So this is what we're stuck with. And we briefly discussed the fun history of why the names counterclockwise and clockwise came about, because of the sundial, and the shadow goes around in the clockwise direction during the day. And let's see. So, we also introduced the concept of negative angles. We have to watch it with that. If we go in a counterclockwise direction, the angle that we define is positive. So like here, for example, we go around through 2 quadrants and halfway into the 3rd quadrant to come up with the angle 225 degrees. But if we went in the clockwise direction, we would be going essentially backwards 135 degrees. So that is defined as negative 135 degrees. It's a little strange to think of negative degrees, but if you're not moving in the counterclockwise direction, the angle is said to be negative. So as you can see, though, either way, you're ending up at the same final location. So that means that 225 degrees and negative 135 degrees refer to the same thing. And so they're said to be coterminal. And if you forget how that works, just remember the absolute value of these two numbers has to add up to 360. All right, so we do have negative angles. Now, also, we can have angles that are greater than 360. For example, if you went around the entire circle twice, that could be considered 720 degrees. So the angles that are larger than 360 can be reduced to angles between 0 and 360 as well. All right, so let's jump ahead. Then we remember radians. The formal definition is that 2 pi radians are 360 degrees, which means that pi radians is the same thing as 180 degrees. It's kind of a nuisance, but for certain applications, it's easier to think about radians than degrees. Also, just remember 1 radian is equal to about 57.3 degrees. All right, so finding coterminal angles, which we just discussed, angles that end up with the same terminal side. So again, you can see that going counterclockwise brings us 140 degrees to this line, or ray, I should say. Going clockwise, we're going 220 degrees in the opposite direction. These two bring us to the same point, therefore they're said to be coterminal. And as we predicted, their absolute values do add up to 360. So that they mean the same thing. So if you took the sine of 140, it should give you, in fact, let's prove this on our calculators. The sine of 140, I don't know what it is, but let's find out. I'm going to do that right now. The sine of 140 is approximately 0.6428. If I do the same thing for 220 negative, it is in fact the same thing. So the calculator is able to tell that both of these mean the same thing. Very smart calculator. Oh, you know what? I just noticed there's a button in the bottom left-hand corner, RAD, that has to represent radians. Wow. Let me just try something here. I think I have discovered how to do radians on your calculator. Let's try it as an experiment. So first of all, let's go back to that chart we had here. The sine of 90 is 1. Let's go to the calculator and prove it. 90 degrees sine is 1. Wait a minute. My calculator is not giving me the right answer. What's going on here? Oh, for God's sake, the calculator. Okay, I'm starting to lose my confidence in this thing. Let's go back to that chart we had, 90 degrees. The sine of 90 is this angle right here. If I try to calculate the sine, oh, you know what's going on here? The opposite and the hypotenuse are the same side. So the sine of 90 is defined to be equal to 1 to 1. But on my calculator, I'm typing in 90, and it's not giving me the right answer, and I'm getting very annoyed. No, it's not catching on, and I'm not sure why. That's very annoying. Oh, I know what happened. Sorry, my fault. I hit the wrong button. Okay, I apologize to the calculator. No, it's all set. Sorry, my fault. I hit the wrong button. 90 degrees, sine of 90 is in fact 1. But let's try an experiment. We know that 90 degrees is pi over 2 radians. Where is that? There it is. So as an experiment, why don't we try to calculate the sine of pi over 2? Now, how would you do that? Here's what you have to do. First things first, go to the bottom left-hand corner, and you see that rad button down there? That means radians. Then in the bottom right-hand, or sort of not the bottom right-hand corner, the bottom of the center, there's a pi there. Hit pi divided by 2 equals. And then when all of that is done, actually, let me write down these steps. Might as well sneak it in right here. Let's sneak this in right here, right now. So I think this will be very helpful to you, having access to this. The sine of 90 degrees is 1. On the calculator, this is implemented as, what I should say is not on the calculator, on the iPhone calculator, this is implemented as 90 sine. Okay, but since pi over 2 radians equals 90 degrees, the sine of pi over 2 obviously equals 1 as well. So on the calculator, you would hit the radian button and then hit the pi button. But you have to hit over 2 equals and then hit the sine button. All right, so hit radians, pi over 2, pi divided by 2 equals, then you hit the sine button. and it does come back to 1. All right, so those are your keystrokes: radians, pi over 2 equals, and then sine. Now, by the way, here's a helpful hint. Don't forget to turn off that radian button, because otherwise you're going to louse up all your following results. Okay, so in other words, once you hit that radian button, it stays on. When you hit the radian button the second time, it goes back to degrees. So don't leave it in the radian mode. It would be easy to forget about it and then make a mistake. We do not want that, do we? No, we most certainly do not. All right, well, that's very helpful to know. All right, now, let's see, what else do we need to review? We had a little more terminology that we introduced. Remember, we looked these up. An acute angle is less than 90, a right angle is exactly 90, the obtuse angle is more than 90 but less than 180, a straight angle is 180, and finally a reflex angle is between 180 and 360, because presumably 360 would be another straight angle. All right, and what else do we need to review? Let's say, complementary angles that add up to 90, supplementary add up to 180. It's not that big of a deal, but if you run into these words, you don't want to have to be constantly looking them up again. All right. Oh, yeah, and I just want to remind you that when we have very large angles, larger than 360, 740 is equivalent to 20, because you're just going around the circle twice and then 20 more degrees. So the reference angles are the angles between 0 and 360. Anything larger than that can be converted into a reference angle by subtracting either 360 or 720 or some multiple of 360. The same thing holds with radians, except that we're now looking at 2 pi radians. For example, 7 pi radians is the same as pi radians. Okay, because you subtracted 2 pi 3 times, meaning you went around the circle 3 times plus radian, 1 more radian. All right, now, here's where it's going to get interesting. We're going to introduce a very important idea for how do we calculate the sine, cosine, and tangent, but we're going to do it in a way that we can figure it out without having to memorize it. So we start out by looking at a circle, and we note that the area of what we call a sector, meaning the shaded region, is 1/2 of theta times r squared. Now you might say, well, who cares? What's that for? Don't you worry, it'll come in handy in a minute. Okay, so 1/2 of the angle times the radius squared. Remember, this is the radius. And you might also recall that the radius is 1/2 of the d, where d is the diameter. The diameter goes all the way across the entire circle. Okay. So the radius is only restricted to that one quadrant. The diameter cuts across the entire circle. One of them is twice the other. Now, if you notice, the r has to be squared here because this is area. It's measured in squared units. So what are we going to do with this information? Good question. So we're going to introduce a very special circle, which will get a lot of mileage out of, and it's going to be given the very mysterious name, the unit circle. And all that means that the circle starts at 0, 0, and the radius is 1. Now, of course, the radius is the same no matter where we draw this line. In other words, if I drew it here, it would also be 1. So the radius is 1, the center is 0, 0. That makes things a lot simpler for our calculations. So think of this as the word unit, the unit circle, where the word unit simply means 1. Radius is 1. All right, now what are we doing with this? Let's start by using this information to calculate sines and cosines. And of course, well, here's another example. We just did this, but that's okay. Let's look at this thing. So here I've got the sides labeled as A, B, and C. And of course, remember our old friend, the Pythagorean theorem. Is that A squared, everyone remembers this, nobody forgets this one. Okay, and you can see that's true here. 1 squared plus radical 3 squared is 2 squared. Now, looking at this theta angle here, it should be clear that the sine of theta, remember, is opposite over hypotenuse from our SOHCAHTOA mnemonic. So in this case, the sine is A over C, or 1/2. The cosine is B over C, which is radical 3 over 2. All right, so this we know. Just a little more review. Now, here's the interesting part. We're going to put this inside of our unit circle. In other words, we're going to describe a triangle, a right triangle inside of our unit circle. All right, here we go. So you can see that if T is the angle of interest, with respect to T, the sine is the opposite over the hypotenuse. So sine T, opposite over hypotenuse. Now, the hypotenuse, because this is the radius circle, h equals 1. Since this is a unit circle. So what that means is that sine T equals O over H, sine T equals O over 1, or that means the opposite is the sine of T. And it's labeled that way right here. In other words, this blue line is the sine of T. So for example, if T is 30 degrees, we've already determined that the sine of 30 is 1/2. All right, the sine of 30 is 1/2, which we confirmed in our calculators. So that means that blue line would have a height of 1/2. And based on the same reasoning, the cosine of T, which is A over H, or A over 1, implies that A equals the cosine of T. And if this was 30 degrees, that would be, as we saw before, radical 3 over 2. So that's where this is headed. So basically, the triangle is set up so that no matter what points we choose on our circle, that defines a unique angle T, and this blue line, this horizontal blue line, is the cosine of T, and this vertical blue line is the sine of T. Okay, and of course the hypotenuse is just 1. Well, how does that help us, you might say? All right, well, what this also implies is that x itself is simply the cosine of T. Y is the sine of T, which in this case would be, if T is 30, then this point we have here is radical 3/2, comma 1/2. All right, so on the unit circle, depending on the angle that we define here, this point is itself nothing but x cosine of T, y is the sine of T. All right. So it's very bizarre and abstract, but don't worry. After we do a few of these, you'll start to get used to it very quickly. All right, so let's see, where are we? Let's try an example. Let's look at this one. 45, this is a 45, 45, 90 right triangle. And remember, with the unit circle, S is the cosine, X is the cosine, which in this case is the cosine of 45, and Y is the sine. All right, it's always cosine, sine. Okay, so just remember that. X is always the cosine of that angle. Y is the sine. Now, here's the thing. We want to know what those values are. But the only thing we know for sure is that because this is the way it's set up, the only way that these two angles can be the same is if x equals y. So since the angle, this angle, I mean, right here, is 45 degrees, that implies that the one in the upper right-hand corner is also 45 degrees. This implies that x equals y. They're both the same number. Now, the Pythagorean theorem tells us that a squared plus b squared equals c squared. So we can think of these as, or actually you can rewrite this as x squared plus y squared equals 1 squared. All right, that's the key to the whole thing. This could be thought of as side A, this could be thought of as side B. 1 is the hypotenuse. Okay, so this is A, this is B, and this is C. So therefore, we know two things. X squared plus y squared equals 1, and x equals y. So we actually have two simultaneous equations that we can solve now, right? So let's remind ourselves, we just determined that x squared plus y squared equals 1 and x equals y. So what we can do is we can plug in x for this y. We did that right here. And so what this is telling us is that 2x squared equals 1, x squared equals 1/2, x is radical 1/2, or So we'll simplify it a little bit. So what this is telling me is that x, the cosine of 45 degrees, is radical 2 over 2. And since x equals y, that implies that the sine is also radical 2 over 2. So we end up with a right triangle that looks like this. Maybe I'm trying to like, maybe that's a little too small. Let me draw it in the next slide. Oh, let me draw these. Like they've been using blue. I think that's a good idea. So that's our x. This is our y. And we know that this is 1. So it's the triangle itself follows the Pythagorean theorem. And the sides are radical 2 over 2, radical 2 over 2, and 1. So basically, the circle itself is telling us that the cosine of 45 is radical 2 over 2. And this is just straight ahead geometry. In fact, this is how the early Greeks proved everything. They used only geometry. Algebra wasn't really well developed at that time. Math was considered to be geometry. And so anything they needed to demonstrate was always going to be done with a format like this, where they're using angles and, you know, trigonometric functions to solve for whatever they were looking for. So we go back to that chart we were looking at earlier on the internet. You'll see that y, what do you know? 45 degrees, sine and cosine, both radical 2 over 2. So in other words, now you know why. Because they represent the two sides of a right triangle with a hypotenuse of 1, where the angles are 45 degrees. That's the reason. Okay, so you can memorize that if you want to, but you don't have to if you understand what we just did. Now, having said all of that, sure, you got your calculator, but it's nice to see why these results are what they are. And again, it's all being derived with geometry. So now 30 degrees is a little bit trickier. Here's what you have to do for 30 degrees. We need a 30, 60, 90 right triangle for that one. Okay, now no matter what angle we're doing here, this is always 1, the unit circle. This is the cosine of 30. And this is the sine of 30. The question is, what values do we have here? How can we figure out, we've got the 1, what about the other 2? Well, this is where it gets a little tricky. What they've actually done is they have drawn triangle, which if you notice extends down into the fourth quadrant. Why did they do this? Because they wanted to create what's called an equilateral triangle. And that means that all three sides are the same, and so are the angles. In other words, it's true that this angle is 30 degrees in the first quadrant, but when you combine these, you'll notice these add up to 60 degrees. So you've got 60, 60, 60, and that means the sides are R, R, and R. Okay, so, and then that also implies this is Y. Y is actually 1/2 of the radius of the circle, which means it's equal to 1/2. R is 1. Now, again, because this is an equilateral triangle, what do we know? And by the way, this implies that the sine of 30 degrees is 1/2, which we already know. What about the cosine, though? Well, for that, we can use the Pythagorean theorem. So let's just call this x. So we know that r squared plus x squared equals y squared within this top triangle. But we know 2 of the 3 values. Okay, so in other words, we already know that r is 1 and that this is 1/2. So we've got 1 plus x equals 1/4. Ooh, something's not right. Hold on a second. No, I obviously did something wrong. The hypotenuse here is r. So I've set this up incorrectly. Sorry. It's r squared equals x squared. That's why. Okay. All right. So remember what we're looking at here. We have within the first quadrant, we have r squared, or just r. Let's put it that way. R, x, and y. That's better. So in other words, remember r is the hypotenuse. So x squared plus y squared is r squared. But again, we know that y is 1/2 and r is 1. That's better. X equals 1/4. X plus 1/4 equals 1. X equals 3/4. And so what this is saying is that the sine, the cosine is radical 3/4. Now, radical 3/4 can be written as radical 3 over radical 4, radical 3 over 2, right? So what we just demonstrated is that the cosine of 30 degrees is radical 3 over 2, which we just got through proving a little while ago on our calculators. So that one was kind of a mess, but we got it. Okay, so in other words, the whole idea here is that you can figure out the cosines and the sines of 30 degrees by describing an equilateral triangle, but it does have to spill over into the fourth quadrant. So it's a little bit messier, but there it is. And then you can, 60 is even worse. So somewhere in here, I've got a picture that will help you very much Well, this is just a table. I put this together myself, but here's what I was building up to. If you kept doing this, you would eventually fill in this entire unit circle diagram. And you can use this as reference on your test. This one, for example, this point means that the cosine of 30 is radical 3/2. The sine of 30 degrees is 1/2. But remember too, this also is the same as pi/6 radians. And so we did this ourselves. 45 degrees, we did this ourselves as well. So this implies that the cosine of 45 is radical 2/2. The sine is radical 2/2. We move up the circle. If we did the same thing with 60, the cosine is 1/2. And the sine is radical 3/2. And then we move up around the clock here, so to speak. For 90 degrees, the cosine is 0 and the sine is 1. And then we move our way around, and all of these can be calculated from this unit circle. But we know now where these are coming from. In other words, we understand the geometry behind each one of these. We're not just memorizing it, we're understanding where these numbers are coming from. Now, you're not going to be asked to do this yourself, but you would like ideally to understand what the unit circle is all about and how it's helping us calculate these trig functions. Okay, so anyway, now the next thing we want to look at is we can never seem to get rid of domains and ranges. The domain for the sine and the cosine is all real numbers. The range is bounded between -1 and 1. In fact, why don't we prove this by going to Symbolab and looking at a graph of the sine of x and the cosine of x. So so you see what it's doing. It's going through these cycles. Now you can see any number on the real number line is acceptable. The domain is every possible value of x. But if you look at this graph carefully, it never goes above 1 or below -1. That's why the range is bounded between 1 and -1, including those two values. What about this cosine? Whoops, I think I got the letters backwards. And if you look at it very carefully, same thing. It cycles up and down between 1 and -1. And the domain is the entire real number line. Now, this is not going to hold with the tangent. There's at least one value where the tangent is undefined. Let's take a look at the tangent. And let's see what it looks like. Aha. So you can see there's actually multiple places where it cannot reach. So the tangent does have several asymptotes. So the domain it looks like the domain is the entire real number line. It's the range. Let's see, the range. No, wait, hold on a second. It should say it right here. The domain is, oh my God. Well, all right. So it's the domain where there's pieces missing. The range is everything from negative to positive infinity. All right, and then the others are just functions of these. Now, by the way, yes, so here we're just once again revisiting these definitions. These are all based on the rest of them. By the way, this is what you would have to do based on your unit circle. remember the cosine is x, the sine is y. The tangent would therefore be y over x. Okay, so we go back to the unit circle for a second. If I wanted to know the tangent of, let's say, 30 degrees, it's the cosine over the sine. Radical 3 over 2 over a half, which is just radical 3. Okay, so in other words, it could be done. In other words, you may have wondered, well, we've got all the sines and cosines. Is that all we need? Well, it turns out that yes, that is absolutely correct, because all the other trig functions can be derived from the sine and the cosine. As we saw here, oh, wait a minute. Oh, God, I think I got it upside down. Sorry. Sine over cosine. Let me fix that. The tangent is the sine over the cosine. So therefore, for 30 degrees, it would be 1/2 over radical 3 over 2, which is just 1 over radical 3 or radical 3 over 3. So that's all you would need to do. What about the others, though? Well, okay, remember, they're all based on the first three. In other words, the sine, the cosecant is the inverse of the sine. So actually, let me do this on a separate page here. We don't want to clutter this up too much. All right, so since we already know that the cosine of 30 degrees is radical 3 over 2, and the sine is 1/2. That implies that the tangent equals, the twos cancel out. Okay, and then we can also say that the secant is 1 over the cosine. Which is 1 over radical 3 over 2. Okay, the cosecant is 1 over this sine. And then finally, the cotangent is 1 over the tangent. Radical 3. Okay, so that's how you would get it. So in other words, the unit circle is enough for us to calculate any trig function for any of these angles that we choose to define. Now, the circle only goes, in this case, 30, 45, 60, and all the rest. So if you have others, you would obviously have to do something a little different. But it's showing you the relationship between all these calculations so that you can calculate them with geometry if you need to. Of course, we're probably going to use the calculators, but still, it's nice to know that you can do this. All right. Now down here, I've got a nice little chart of our own to help us remember some of these. And I just wanted to show you just quickly before we finish, the Pythagorean theorem is a little bit more general than we maybe generally realize. It turns out that The Pythagorean theorem, as we saw with the unit circle, implies that 1 equals the cosine squared plus the sine squared of t. All right. One cosine and sine, because these are x and y. And so the theorem implies, since 1 is the hypotenuse, this implies that 1 equals cosine t plus sine t. But we can rearrange this to do something similar with the other trig functions in case it comes in handy. So here's one you might not have recognized. If you divide through by cosine squared of t, this is an alternative version of the Pythagorean theorem. You might not recognize it, but this is an implication of the Pythagorean theorem. Interesting. And there's another one here that might come in handy one day. If you divide through by the sine, that also implies this relationship. So now, usually these are used to simplify our results. They're not, it's not that big of a deal, but it depends. If you find yourself with a messy trig expression, sometimes these can help us reduce it to something much simpler. But the most important thing here is the unit circle and how it determines the different trig functions. Now, there's one more thing I just want to quickly show you. Some of the trig functions, you might remember this definition from way back. This setup here, this means that a function is even. And this means that the function is odd. So for some of these trig functions, because they repeat themselves on a regular basis, we have the following interesting results. Okay, so you don't have to memorize these. I just want you to see them. So here, for example, we're saying that the cosine of negative 30 is the same thing as the cosine of 30. The secant of negative 30 is the secant of 30. Okay. What about the others? With the others, it's the other way around. In other words, the sine of negative 30 is negative, whatever the sine of 30 is. And the same thing you can see holds for the others, the cosecant, the tangent, and the cotangent. So again, sometimes this can come in very handy. So it's good to know this. All right, so I think we've covered everything here. There is a chapter 5 problem set. Let's quickly take a look at it. There it is. It's not that complicated. It's nowhere near as painful as it looks, as you might think from what we were doing. So you're going to calculate here, you're just simply going from radians to degrees. Here you're going from degrees to radians. And then here you're literally just calculating these values. And don't forget how I showed you that this could be easily done on your calculator. Reference angles, remember what that means. Let's go find them again. The reference angle is the smallest acute angle that can be formed with the terminal and the horizontal axis. Oh, here we go. Yes, we definitely did this. So within the first quadrant, 135 is equivalent to 45, okay? So you're looking for the smallest acute angle that has the same value. All right. So this, remember this chart, and then this one as well, in order to do reference angles. What else do we have here? Oh, and then here, just solve for these. So look how easy that is. It's pretty straightforward. I mean, it's a pretty scary chapter, but I think you'll find these questions to be not terribly difficult. So that's good. That's quite a relief. And then, so next week we'll do this problem set, and then we can start 11. Now, 11 is a very different branch of mathematics. It involves a lot of counting, believe it or not, and it also involves probabilities. So I think you'll find that to be very interesting. Very different too from what we've done up to this point. More applications to the real world, let's put it that way. All right, so I guess that'll be it for now. Now, anything else? Well, you know, I'm still, don't worry, I'll be getting those midterms done as soon as I can. But other than that, I think we're all set. I don't think there's anything else we have to worry about right now. It's just do the chapter 5 problem set, and then we'll start 11 next time. All right, so I'll see you all next Wednesday then. Oh, there's a chat. I missed it. Sorry. Yes, thank you. You're welcome.
Thank you for class today, Professor.
Okay, sure, absolutely.